Good morning, everyone. Today is our fourth lecture about probability theory and stochastic process. In the previous lecture, we went through very important concepts about probability or about random variables, and we showed that the random variable is like a real number representing the uncertain fluctuations of the physical value that we are looking for, or for any uncertainty. So we use a random variable to map from event space to real number space. After that, we presented several basic random processes, or random variables like Bernoulli random variable and also binomial random variable. And in today's lecture, we continue showing several different random variables. Later on, we will show also some numerical examples, but the most important thing, even more important than the numerical example, that to know that those random models is to represent certain behavior, certain uncertainty behavior in the quantity that we are looking for. So there is some quantity that we like to know to broadcast or for forecasting, but we cannot represent this quantity into like deterministic equation, either like one-to-one equation or even dynamic equation like differential equation, for example, or difference equation if it is discrete. So in that case, we have some uncertainty associated with the quantity that we are looking for. So, however, even there is a lot of uncertainties about it, or there's some randomness associated with it, but all these usually follow certain like behavior or certain trend. Okay, and with this, how to represent or how to model these uncertainties or these random trends. So we use a probability density function or probability mass function or random variable models to represent these uncertainties. So this is what we should like understand from this lecture and these slides. After that, how to solve some numerical problems with this can come later. So this is the second important part, but the most important part is to understand the concept why we give these like models. Okay, so as usual, I will switch to the white screen, or to the whiteboard, in order to write a few things here about these models. Okay, what we can see in front of us, this is one of the models that it is used. It is called Poisson random variable. Okay, in the Poisson random variable, it is quite similar. It is also discrete. It is quite similar to the binomial distribution, but this main difference here. The difference is that when the total number of trials is too large. Okay, maybe I can write here. I will try to. Okay. Yes. So in binomial distribution, as you remember, is what is the probability that we got like k axis or n small axis of success out of n capital trials. So this was given in the previous lecture, that the probability that we got, for example, k or n small, doesn't matter, of success is equal to, we said that if we have n trials, so we will have n factorial divided by n minus k factorial times k factorial. This was given in the previous lecture, and of course multiplied by the probability of success. It is p of the power k, because it means that there was like k independent success times 1 minus k. Of course, 1 minus p is the failure probability of the power of n minus k. So it means that the number of failure was n minus k, the number of success was k, and then we take this probability multiplication. Why we take multiplication? I take you even to the previous lecture, the lecture before the previous lecture, when we say that the probability of any two events, A and B, equal to probability of A times probability of B when A and B are independent. Okay, so I hope that you still remember that. So since A and B are independent, and here we assume that all the repetition of these experiments are independent. Because of that, we got this very well-known binomial distribution. However, there are some cases where the number of trials is too large. For example, n can be millions, for example. Okay, and k can be sometimes even small, can be 2, 3, 4. Okay, and the probability of success can be also very small. The probability can be very small, and 1 minus b can be close to 1, and b can be close to 0, or the reverse, or b can be close to 0, b is close to 0, and 1 minus b is close to 1. Okay, so in that case, this binomial distribution cannot work. Why? Because of several reasons. First, that if you want to take n for large number, to take the factorial, usually it is not possible to calculate. I mean, even if you try now with your calculator to compute like 200 factorial or 300 factorial, it will not work. What if we talk about n of millions, for example, or thousands? So this equation is not working in that case when n is very large and b is very small, or the reverse, of course, or b is close to 1 and 1 minus b is close to 0. So in that case, this will not work. What is the alternative for that? The alternative is this Poisson random variable. So the Poisson random variable, it is also related for independent, okay, process or independent random variables. That what is the probability that we got I out of success? Okay, and in this one we don't have like n number, but we have lambda. Lambda here is the average of like occurrence, the average of occurrence. We will revisit Poisson random variable several times later, but now it is enough just to represent it in this way. So the calculation is I mean very easy. Just you need to substitute in this equation. So if you got any problem where you have the average number of success is lambda, and then what is the probability that you will get I success, so you can just multiply this. And also there is some derivation of this Poisson random variable from the binomial random variable. It is given later in these slides, but it is good that if you follow it, it gives you some concepts there. And we will follow anyhow, anyway. We will see it later. So here you can see in this example, suppose that the number of typographical errors in a book has a Poisson distribution with parameters lambda equal to 2. So the average rate of errors is 2. Calculate the probability that there is at least one error in the book. What is the probability that there are exactly 10 errors in the book? So the probability that you will have at least one error, it will be 1 minus probability that x, there is no error at all. So if substitute with I equal to 0 in the previous slide, if you put here I equal to 0, lambda of the power 0 is 1, 0 factorial is equal to 1, and here you will have e minus 2, as you can see it here, e minus 2. So 1 minus e minus 2 is equal to 0.8647. So the probability that we will have at more than one error, it will be about 86%. And the probability that we will have exactly 10 errors, it will be 2 of the power 10. 2 is lambda, the power of the power 10. So it is just direct substitution in the previous equation. But I will give more sense and more physical meaning for these calculations later. Okay. Here is the derivation of this equation. And the idea here that Poisson distribution can be used to count the number of random events in time. Okay, now let us give this physical meaning for this. Assume now that what is the probability that the computer that now you are connected to the lecture today, that it will fail. Suddenly it will destroy the computer, and it will have some malfunction and will switch it off. What is the probability of that? Now, if I asked you, what is the probability that the computer will switch it off because of malfunction or because of any fault in the computer? Okay. Now, this question, we have some uncertainty. We have some uncertainty about this question. Okay. We have two uncertainties here. What is the probability that you will have this computer to be switched off like within the time of the lecture? We have like online lecturing about 2 hours. What is the probability that you will have malfunction or switching off of the computer within 2 hours? So we have uncertainty here. It can be like 1%, it can be 5%. It depends on the some like measurements or previous reliability of these computers. Okay, and then if we ask it, what is the probability that this computer will be switched off because of malfunction like 2 or 3 times within 1 month? So this is another question. Let us take another example. What is the probability that the lamp in your class right now, it will be burned out? Okay, and what is the probability that it will burn out like 5 times in month or 5 times in a year? Okay, all these questions now, they convey some kind of uncertainty. Okay, Poisson distribution is the way to compute this probability, given into consideration that all these processes are independent, and also it doesn't depend on the history. Okay, I give you example. If the probability of the certain lamp to be like to burn out, okay, let's say the probability is to be 0.1 within 1 month. Okay, now what is the meaning of 0.1 within 1 month? It means that there's 10% that the lamp will be burnt out, will be malfunction, will destroyed within like 1 month. Okay, now you installed the lamp. Okay, after 2 months the lamp was working fine for 2 months. Okay, now after 2 months you want to calculate what is the probability that this lamp will switch it off or will burn out within the next 1 month. It will be still the same, 0.1. Okay, you come after 1 year, the lamp is still working. Okay, what is the probability that it will burn out within the next 1 month? It will be the same, 0.1. So the Poisson distribution is memoryless. As far as something is still working, the future does not depend on the history or in the past. Okay, so you need to remember this fact about this Poisson distribution. Okay, now assume that you are looking for something that might happen randomly in time. As I said, for example, the burnout of lamp, switching off of this computer that you use, or maybe someone comes to your class right now visiting you. Anything that it can happen randomly in certain instance of the time. Okay, now we are here, we are looking for the future. Okay, this is the future. T equal to 0, it means that our current time. Okay, now we are looking to the future. These events, these random events can be happen at any time. Okay, it is like death. Death can happen at any time, we don't know. So this can happen at T1, for example, we call it as T1. Then the same event can happen at T2, it can happen at T3, and so on. So there is something that can happen several times. Of course, death happens only once for a human being, for per person. But other things, for example, if it is lamp, so the lamp is switched, is burnt out, you change it, so it might happen again and again. So it can happen several times. Or something that if someone enter your classroom right now, for example, this is a random thing. So maybe they misallocate their own student, their own classroom, and they just come to your classroom, go out. After some time, some other students might come, sometime other students might come. So these are random events. These are random events might happen at random instances of time. Okay. So the question here, what is the probability if the rate of this coming, based on the history, for example, we found that the rate of this coming is 5 students, or 5 times that the lamp, one lamp, it might or 5 lamps might burn out within, let's say, 1 month. In your case, for students, maybe 5 students per day, they might by mistakenly they open your classroom right now. So this rate is called lambda. Okay, now what is the probability that we will have exactly 2 students try to come to your classroom by mistake? Okay, so now you can calculate it based on this equation, okay, on this Poisson distribution equation. What is the probability that in your classroom right now, I can see that you have 3 or 4 computers connected now to the lecture. Okay, the the uh, the length of the lecture is 2 hours. Okay, what is the probability that 2 of these computers will be switched off during the 2 hours of the lecture? Okay, even at different times, no problem, not necessarily at the same time, but 2 computers will be switched off during this lecture during 2 hours. Okay, based on what we calculate this based on lambda. What is lambda? Lambda is the rate of switching off of a computer due to some malfunction. So maybe the lambda is equal to, maybe it can be 0.0001 per hour. What it means, this lambda, it means that 1 per 10,000 computers might have like malfunction or destroyed within 1 hour of working. Okay, so I use this lambda now. How many hours I have? I have 2 hours. Then I need to multiply this lambda by 2. So you can see here, lambda times t. T is watching time, or is the time of interest. So lambda times t is the time of interest. So it will be 0.0001 times 2 hours. And then I am looking for 2 computers to be destroyed in this lecture. So it will be 2. The here is 2 factorial is equal to 2. And then it will be e minus lambda is 0.0001. So 0.0001 times the time is 2 hours. Actually, this equation is very important, and actually it is extremely important in case of reliability. There's a topic is called reliability engineering. It is very important topic in many industrial sectors, like for example in electrical engineering, also in communication, in many different areas, when we need to keep the continuity of operation of certain like a critical process to continue even some failure has happened. Okay, so in this case we use a lot this Poisson distribution in calculations of probability. Okay, for example, we make add some spray, or we can, for example, we will come later about this. We will come later because we have some examples about reliability as well. Okay. Yes. Here we can see the derivation of this Poisson distribution and from binomial. As I explained before. So we are looking within certain time. This time is time t. Okay. And what we did here, we divide this time into short times. I call them here S. Okay, everyone is S. And this is very, very short time. So S is going to 0 second. Okay, is going to 0 second. It's very close. It is close to 0. And then we divide this time into T divided by S, because it's S going to 0. This will be N, and N going to infinity. So N is very large. Okay, and you can see here that S will be T divided by N. Okay, and they are small enough that the probability of any success to happen is equal to B. So the probability, there is no chance to have 2B to happen in one time slot, because the probability here is also very small. The probability of success or of failure per time slot is also very, very small. So then the probability to have two failure in one time slot is almost 0. So there is only one possibility to have failure in this very small S. Now I applied directly, I applied this binomial distribution. As you can see, we have N here goes to infinity. Okay, I am looking for what is the probability that we have K failure, for example. Okay, and this P is also goes to 0, it's very small. And then N minus K goes also to infinity, because N is very large. Okay, then I start to compute this. What is P? P actually is nothing but lambda T divided by N. Why? Because lambda T is the average rate of this success to happen. As I said, that for example, what is the probability that you will get five failures within this period of time T? What is the probability that you have 5? Okay, the probability to have 5 is what is the previous average rate of failure. So if the previous average rate of failure was 10 per this time unit, per T, 10 per T, so then the probability, it will be 10. It will be 10 because 10 per T times T, it will be 10. So it will be 10 divided by what? Divided by the number of cases. So the number of time slots here is equal to N, as we said. So it will be 10 divided by N. So it is lambda T divided by N. This will be the probability P of the power of K, okay, times, then we will have 1 minus, this is the probability, because it will be 1 minus P. So 1 minus P, as we said, P is lambda T divided by N, okay, of the power. This is the probability P of K, but here the total will be N minus K. Okay, so there's no K here. This is just N minus K. And then N minus K, I take the K here, and this is N, and then using this limit theorem. This is the reason actually in the first quiz I put some simple calculations, because I know I'd like to motivate you to revise some basic math, like math 1 in the university. So it is important to revise this limit theorem, probability, differentiation, integration, because we will use them in this course. So this is the limit that we have this representation, and then after substitution we got the result of the Poisson. But in the quizzes and as well as in the exam, I will not bring such kind of derivation, so you don't need to be worried about these derivations. The importance here is to understand that this Poisson is actually coming from the binomial distribution after some under some conditions or assumptions. Another random variable or some uncertainty, that if you have like total number of items that they are n, so you have n items. Let us say that okay, I like to bring some like example which could be easily to understand. Okay, now assume that we have sea, for example, Mediterranean Sea in the front of Benghazi. Okay, so and this sea up, let's say up to 10 kilometers. Okay, we have different kinds of fishes there. Okay, so we have different kind of fishes there in the sea. Okay, um, now we might have some estimation of the number of fishes there. So according to some estimation, you know that using some like ultrasonic radars, you can have some estimation of the number of fishes there. Assume that we divide those fishes into two kinds. Um, Maybe kind one or kind A, and the others are kind B. So we divide those fishes into two kinds. We are interested in A, and all other fishes we put them in the under another category is B. Okay, and uh, so what we have done, um, we take samples from the sea. Let us that we take like 20, sorry, 20 fishes from pieces from the sea. Okay, we fish them, and then we count how many numbers of kind A out of 20. Okay, for example, we found that A out of 20 is equal to, the probability was 2, or they were only 2 fishes from kind A. So the probability that to have A out of this 20 is 22 divided by 20, and this equal to 0.1. Okay. Um, Hypergeometric distribution, it says that if if you have any two kinds of any items, and you take sample of these items, and the number of sample that you take is m sample, in this example is 20, so m here is equal to 20. Okay, and then uh, uh, the number of one of those kinds, A or B, was A. So what is the probability that you will have A? In this case, we have two actually. What is the probability that you have A? K of A plus A is equal to the K out of M times N minus M. N is the number of total number of population. Okay, and M is the kind A, the number of the sample of kind A out of N minus K. Okay, and divided by N out of N. I will give you another example, and actually there's one example in the book that I sent you. There is also another version. I will update you with the latest version of that. I gave in that book one another example related to a process of detecting some contaminated cans. For example, assume that uh, um, one country, they import, for example, ships of or shipments of certain cans. For example, milk can. Okay, milk cans. So, and every shipment, it has, let's say, 10,000 can, and on the harbor we have, let's say, 10 shipments. Every one, it has 10,000 cans. Okay, and everyone, it came from certain manufacturer. This is from manufacturer A, B, C, or from different countries, for example. And we had like news, or we had some information that one of these companies have a 20% of their cans, they have like illegal substances which can cause some like health problems. 20%. only in one of them, not in all of them. Now you would like to check which one have this contaminated cans. Okay, of course it is not possible that to check the 10,000 from every shipment. It will take a lot of time. You will destroy a lot of cans in order to check, and many other problems. Okay, so now I ask you a question. Find the number n, the number m of those cans that you will sample from each of them, in order that the probability to discover at least one contaminated can to be 95%. How many cans you need to sample from each shipment? Okay, so you start from the first shipment, you take this number, which can guarantee that you will get 95% of probability that you will find at least one can with this illegal substances in your exploring. Okay, so you start with the first shipment, and then you go to the second shipment and go to the third shipment until you find that one. But I need to check that the probability to find it is 95%. After solving this, I will update you with the book. After solving this, and I maybe during this lecture later, we will solve it together. So we find that we need to check only 11 can. So if you take only 11 can from each shipment, you will be able, if this shipment has that contaminated cans, it will be 95% that you will cover it. You will discover it. Okay, so you need only to check 11 can from each shipment. So this actually model gives us some a tool to quantify our uncertainty to find that illegal company or illegal shipments. Okay, so the idea here, as you can see, a sample of size n is drawn. So we took n is drawn without replacement from a population of size n. So n capital is the total number. So the total number here we have 10,000. Okay, n is the number that I am looking to find. Okay, composed of m individuals. So we have m from kind A and n minus m from kind B. So here in this example, every shipment, it has 10,000 cans. So m will be 2,000 because 20%. 20% will be 2,000. N minus m, it will be 10,000 minus 2,000, it will be 8,000. Okay, and then if we take this, if we draw n sample, what is the probability that you will find k from sample A? Okay, now I am looking that I like just to detect at least one can. So in this case, I am looking for the probability of x to be greater than or equal to 1. 1 out of n small. And this will be 1 minus probability that k equal to 0. Okay, and after solving this, we can find the result. And also in the book, I simulate the situation, and we found that the case was very similar. So the result is almost like identical between the analytical calculations and also the simulation. In the case of continuous random variable, we explained also, or we discussed the continuous random variable last lecture. And we said that in this case, we have probability density function, because in this case, actually, it is discrete. So we have probability mass function. Here also with Poisson is discrete. So another time we have discrete or probability mass function because it's discrete. But in general, for the continuous case, we have we have the probability density function, as we can see it here. And in order to calculate the probability in case of continuous random variable, then we need to calculate or to compute the area under the curve. Okay, let me search the whiteboard. And now, in case of continuous random variables, we have the probability density function, as we can maybe draw it somehow. Sorry. Yes. So we can draw it. For example, we assume that the probability density function is something like that. This is f of x, and this is x. So this is the probability density function. We have different shapes of probability density function. It can be like pill shape, like this, if it, or maybe Gaussian distribution. It can be like uniform, like this. It can be exponential, like that. So we can have different kinds of random probability density function, each one representing certain trend of this randomness. Okay, each one representing certain trend. For example, if you take this probability density function of x, and now assume that this is a signal with t, and this signal following this Gaussian distribution, then you will find the signal something like that. We might have some peaks, and but very rare to have peaks. And uh, uh, if you take the average here, will be zero, or it will be the mean of the signal, and so on. So now, if you have another signal, it is random. This is x, but let's say that it has uniform distribution from -5 to 5. Then we will have another random signal, but it will be completely different, because now the signal is only between -5 to 5, and the behavior of this randomness can be different. Of course, now I am just drawing something like that. So it can be a random signal, but it is a random signal, but it should follow the uncertainty model here. If we have this exponential distribution, then the signal will have also different shape. Uh, you can see the highest probability here to be close to zero, and the signal, it is clear that it is always positive, as you can see. So the signal cannot be negative, and it is most of the time is close to zero, but it can be also like large signal, okay? But it is always positive signal, and so on. So actually, sorry, there's no negative here, because the signal here, it shows that it is always positive, so it will be all the time positive positive signal. So you can see that in every, and this concept is very important to remember, that every probability density function representing the trend of the uncertainty, or the randomness of the behavior that we are studying or we are exploring. So it depends on this shape. We will have different trend of the randomness of each signal. Okay, this is the first thing. The second thing about every probability density function f of x, okay, we should remember that this is representing a probability, so it must be always a greater than or equal to 0. We don't have a probability density function to be negative. For example, if I give you this shape and I asked you, is this possible to be probability density function, this f of x, directly you will say, no, this is not possible. Why? Because we have negative part here. And it is not possible to have negative part in the probability density function. Probability density function is always positive. This is important because we don't have negative probabilities. Okay? I will remove this. The other thing that we should remember that the integration from minus infinity to infinity of f of x for any probability density function dx must be 1. Because now in the continuous case, the probability density function representing or is working the same way as the sample space in the discrete events. It works in the same way. So the total probability must be 1. Must be 1. Okay. For example, if we take this uniform, let's say from -2 up to 5. Okay. So the probability of this of x. So again, probability of f of x dx from minus infinity up to infinity. Of course, we have nothing from less than 2, and we have nothing after that 5. So it is equal to 1, but it is also the same as from -2 up to 5. F of x dx is the same, is equal to 1. So it is the same because it exists only from -2 up to 5. Okay, so this equal to 1. And we know that the area is equal to 1, and the area in this like rectangular shape is equal to the width times the height. So the width here is equal to 7. So the height must be 1 divided by 7. So in this case, f of x must be 1/7. In this case, from -2 to 5, it will be 7. So it will be 1 minus 7. Okay. What else? In the probability density function, we might have what is known as symmetric distribution. What is the symmetric distribution? For example, if we take the Gaussian distribution, so if we take the Gaussian distribution like this one, okay, so here the middle of the Gaussian or the normal distribution is called the mean here. Of course, not necessarily that always the peak is mean. It is not necessarily always truth, because this is for Gaussian. But for example, if we take Rayleigh distribution, the peak is not the mean, but the peak is always the mode. The peak is always the mode. But in case of Gaussian distribution, mode is the same as mean and is the same as median. Okay, so in Gaussian distribution, the total area is equal to 1 also. So because it is symmetric, so it will be divided 50-50 around the mean. It means that the integration of this distribution of the probability of the Gaussian distribution or normal distribution of from -infinity up to the mean dx is always equal to half, and the integration from -infinity up to infinity of x dx is equal to 1. Take this as a rule. So the area under the probability density function for any random process or any random variable, the total area is always equal to 1. The total area is always equal to 1. Okay. So those are very important features of probability density function. And again, I repeat this important concept. Probability density function is the model that represents the randomness trend in the physical quantity or in the behavior that we are looking or we are exploring or we would like to forecast. If we find the probability density function of any process, then we will be able to find the probability of this random variable to happen. Remember, those are concepts. Now I am talking about important concepts. for any process which has a probability density function given by f of x. Okay, if I asked you what is the probability that x in the future will be greater than or equal to x1 and less than or equal to x2, actually it becomes just normal analytical math. So it is just integration of from x1 to x2. Of course, here we assume that x2 greater than x1. From x1 to x2, f of x dx is simple like that. Is simple like that. You can find in the book and also in the slides that sometimes we put here also x. The reason of that, because later we can use this f to represent different random variables. For example, we can have like f of x, for example, of a, because we have two random variables. So I'd like to represent that if this is for x because we might have another random variable y. Okay, so to differentiate between x and y, I put the random process or the random variable also here outside this bracket. So now this is the probability that we can write it in this way. This is the probability that x to be greater than or equal to x1 and less than or equal to x2 is equal to the f of x dx from x1 up to x2. Don't worry, I will give you a lot of numerical examples here because they are important concepts. But I like to, maybe we will take break after a while. So after the break, we will take several examples, numerical examples. But now I like you to be that like focusing on these concepts, okay? In the previous lecture, I mentioned also about the cumulative distribution function, and we said this was given as f capital of a, and we said that it means that the probability that x to be less than or equal to a. Okay, this is a general, and this CDF, it can be for continuous and it can be for discrete. For discrete, it will be summation. For continuous, of course, it will be integration, and this integration will be the integration from minus infinity up to what? Up to a, because x less than or equal to a f of x dx. Okay, now if I go another slide here, if I have, let's say, any distribution, I don't care about the distribution, so some distribution like that, okay, and I want to calculate the probability, this is x, okay, and I like to calculate the probability to be, let's say, from x1 up to x2. What is the probability that to be between x1 and x2? And this is f of x. Of course, the probability will be nothing but the area under the curve. Okay, and as I explained just now, it is the integration from x1 to x2, okay, f of x dx. However, it is very important to remember, what if you have f of x? What if you have the CDF of this distribution? If you have the CDF, you don't need to recalculate it in this way. So, some problems can be very complicated to calculate the integration. So if you have f of x, you can use f of x directly to calculate the probability. But how? It is very simple. F of x1, what is f of x1? F of x1 is the probability of x to be less than or equal to x1. So f of x1 actually will be this probability. Let me maybe take another color. Okay, so the probability of fx1, it will be this one, up to infinity. This one is the probability of x less than or equal to x1, which means that this one is f of x1. Okay, what is the f of x2? Is equal to the probability that x to be less than or equal to x2. So this one, if I take another color, Okay, I will take maybe this one. So now this probability to be less than or equal to x2 will be all this part, all this part. So all this path from x2 up to minus infinity, all this path is f of x2. Now I want to calculate the probability of x to be greater than or equal to x1 and less than or equal to x2. Okay, now what happened if you subtract the CDF at x2 minus the CDF at x1? Okay, the CDF of x2 will be the area under x2 up to minus infinity. The CDF of x1, it will give you the area from x1 up to minus infinity. If you subtract them, both of them, this part will be removed, this part will be removed, and you will have only between x1 and x2, and in this case, it will be simply f of x2 minus f of x1. It means that this is actually the importance of the CDF. One of the applications of CDF. If I give you the CDF of, or if you know the CDF, you can use it directly to calculate the probabilities. Any probability. If you want to calculate the probability x, for example, if I give you certain f of x, this f of x can be very complicated to be integrated, but I give you also f of x, and then I asked you calculate the probability that x to be greater than or equal to 1. It is very simple because this will be 1 minus probability x less than or equal to 1. Why? From where I bring this one? Because I know that probability of x greater than, x greater than or equal to 1 plus probability of x less than or equal to 1. This means that all range from minus infinity up to infinity, and this range equal to 1. So the probability of x to be greater than or equal to 1 is 1 minus probability of x less than or equal to 1, and this will be 1 minus f of 1. Simply like that. If I ask you what is the probability that x greater than or equal to 1 and less than or equal to 2, it will be simply equal to f of 2 minus f of 1. And you can do it for any kind of probabilities. Okay. I think it is good to have now 15-minute break. Okay. After the break, we will come back with several kinds of distributions f of x, because I know that when you talk only about concepts, it might be difficult to understand how to apply these concepts without numerical problems, as one of you also mentioned in one email to me last time. So this what next I'm going to together, of course, to solve several examples to see how these concepts to be applied. Okay, so now it is 10 it is 11 and 10. Let us take 15 minutes. Okay, so we come back at 11 and 25. Okay.
Okay, thank you very much.
Okay, thanks. Hello again. After the break, we continue the exploring some of the features of probability density functions. Okay, and we have seen already some of those features about the area and the curve representing the probability, and also how to use the cumulative distribution function, the CDF, to quantify the probability of certain event to happen, or certain signal amplitude to be within certain range, and so on. There are too many applications depends on the area. as we mentioned in the previous part of this lecture today, when we talk about reliability, for example, what is the probability that you will get failure in your system, maybe electrical system, electrical generation, or maybe in distribution, or maybe in engine, and there are too many different applications for reliability in telecommunication also. What is the probability that you will receive the signal correctly? What is the probability that you get this symbol in the right area, or what is the probability that it will be shifted to another to be another symbol, and so on. So we have a lot of applications for that. Uh, Before I continue, just now came to my mind about that communication, digital communication, as because all of you from telecommunication area. So in digital communication, actually, we submit not the original signal, but we submit symbols. For example, if it is a binary symbol, then it will be like 0 and 1. We will have every signal or every sample will should be represented like one of the binary signals. It can be, for example, symbol 0 and symbol 1 in this case. So, but to increase the efficiency of the transmission, it is called also like spectrum efficiency. Instead of sending one of two symbols, we can also send 2 bits per symbol. So when we have 2 bits per symbol, for example, 0 0, we send it as symbol 0, 0 1 maybe symbol 1, and then we have like 1 0 maybe symbol 2, and 1 1 symbol 3. So we have 4 symbols to transmit 2 bits. So in each transmission we can send 2 bits. Maybe we can send like as you know that is called 8 phase shift keying, for example, where we can send 3 bits per symbol. So it will be like 0 0 0. It can be S0, 0 0 1 will be S1, 0 1 0 will be S2, until 1 1 1 it will be S7. So here we have 8 symbols to be transmitted. If we take this 8 phase shift keying, then we will have, it will be like the power will be the same for every symbol because we change only the phase. So here we will have this 8 symbols. So symbol 0, symbol 1, symbol 2, symbol 3, symbol 4, symbol 5, 5, 6, and then yes, 7. So now we have eight symbols from S0, and it will be S1, S2, and so on. Okay, there is some kind of distribution of these symbols that to guarantee only 1 bit change it from symbol to symbol. We will not going to describe telecommunication here, but I like just to show you how this probability density function could be applied here. So now when you send symbol 0, for example, if you send symbol 0, due to the noise and multipath, you will never receive it as in the same location. It will be shifted due to noise and due to the interference. So in this case, when you send S0, you might receive it here, you might receive it here, you might receive it here, you might receive it here. So you might receive it in theoretically anywhere. Okay, so you can see here that each symbol here represented by its face, because the power is the same. So the power is represented by the length here, so R. So if this is voltage, then the power is related to V square, for example, or to R square, and the power here is fixed. So in the practice, it means that you submit your signal like x of t, for example, equal to maybe cosine 2 pi f0 t, okay, a plus it can be your transmitted phase, which could be, for example, some factor times pi times the transmission itself, so times the symbol I. Okay, so here the symbol I is changing only the phase, and you can select alpha and the values of I in order to specify the phases. Okay, so for example, in this case, if we assume that this is like uniformly distributed, so or uniform phase, so here we have pi over 2, here we should have pi over 4, and for this one, it will be pi over 4 plus pi over 2, and so on. Here will be like pi, and this will be, of course, the 0 or 2 pi. Now, if you send this signal, as I said, the signal will not receive it as exactly the same. It will be like shifted in the amplitude and also in the phase. And the amplitude, it is not a problem, because here the amplitude is 1 and there is no information in the amplitude. So simply we can use like any we can ignore any changes in the amplitude because we don't have information in the magnitude. The power is the same for all of them. This is not the case, of course, if we use a QAM. A QAM modulation, we have information amplitude and phase both. But in phase shift keying, we have the information only in the phase. So there, we can normalize the amplitude. For example, if we receive it here, no problem. We can normalize it to be here. If we receive it here, we can normalize to be here. So there's no problem about that. Where's the problem then? The problem is the error in the phase. Error in phase causing us for some maybe we are by mistake we detect the wrong like symbol. What I mean, if we receive now, if we divide this by over 2 into 2 parts, it will be here pi over 8, and here will be also pi over 8. Okay, now if I receive the signal here in this area, what I usually how our it is called like correlator receiver. Our correlator receiver, actually, it measures the distance between the received symbol to any of those legal symbols. Legal symbols are S0 and S1 and S2 and so on. So if you receive it here, simply it will measure the distance between the received symbol and one of the real or the legal symbols. So the distance here, it is clear that it is very close to S0, so that it will be correctly detected that S0. Okay, because when you send the signal, the probability that you would, if you send the phase equal to 0, the probability that you will receive phase exactly is 0 actually is 0. It is not possible at all because of the noise and because of the interference, because of multipath. Usually, you will receive corrupted version of the transmission. But what if the noise was strong enough to push the transmitted signal from S0 to be received somewhere here? Okay, so if it was received here, your receiver will measure the distance between this received signal to S0 and to here is, for example, S7. This signal here, actually, it is closer to S7 than S0. Then your receiver will decide that this signal is S7, but actually it was S0. Because of that, we will have error. In digital communication, we will have error. How could we quantify this error? Then we need again to calculate the probability density function P. So the probability density function, what is the probability that your received phase theta I, okay, to be a greater than, or the magnitude of it will be greater than or equal pi over 8, because if it is outside pi over 8, we will have error. Given that the transmitted one was equal to 0 degree, because this is the one we send it at 0 degree, we receive it greater than pi over 2. We can now calculate the probability of error. Theta I will depend on the noise, depends on the channel type. But now we can calculate the probability of error. And we should repeat it for everyone to calculate what is the probability of error in general. So you need to do it for everyone, but because it is symmetric, or in this case, it is symmetric. So it is enough to calculate only for one. And when you calculate for only one symbol, it will be the same for all other symbols. Okay, because it is a symmetric transmission. So this is one application of this probability density function. Okay, let us go back to the distribution. So we have any distribution of x. And now if we take one simple case, it is called uniform distribution. Uniform distribution is any distribution, but it has like equally likely within the range of the changes of the uncertainty x. So it can be, for example, from any value, any value a and any value b. Okay, and it will be like this square shape or rectangular shape. Okay, and here the magnitude or the amplitude here will be 1 divided by b minus a. Why? Because the area must be 1. The area must be 1. Okay, if I asked you the question, what is the CDF for this probability density function? Simply you will say that CDF f at a equal to the probability that x to be less than or equal to a, and this will be the integration. Okay, this is equal to, we take from minus infinity, but we don't have to go to the minus infinity because this is already 0. So we can start from sorry, let us use another thing than a, because a is already used here. So I will take this off. So let us call it x0. Okay, so it will be from a, because this is the minimum, a, up to x0. What is f of x here? F of x, as we said, it is 1 divided by b minus a. So it will be b minus a dx. We don't have x here, so the integration of 1 is equal to x. So it will be like x, and here divided by b minus a, it is fixed, and the integration limit is from a to x0, and this will be x0 minus a divided by b minus a. This is the CDF of the uniform distribution. So if the question that what is the probability that x to be less than or equal to 1, and you have a equal to -2 and you have b equal to 2, you can just substitute here in this equation. So the probability means that it is the CDF of 1 equal to x0 is equal to 1, will be 1. Okay, minus a is equal to -2, minus becomes 2, plus 2, divided by b is 2, minus 2 is equal to 2 plus 2 is 4. So it is 3/4, which means that it is 0.75. And in other words, 75% of cases that x will be less than or equal to 1 in this problem. Okay, so and if I ask you what is the probability that x to be greater than or equal to 1, easily it will be 1 minus probability of x less than or equal to 1, and this will be 1 minus 0.75, and this will be 0.25. Means that 25% of cases that x will be greater than 1, as far as the distribution of this random variable is from -2 up to 2. Okay, actually this uniform distribution is the simplest continuous distribution that you can find. It is just uniform, as you can see. So and here it will be 1/4, of course. Okay, okay, so if you have some generator, random generator, and this random generator is the distribution of the signal continue, or it has the same as this distribution from -2 up to 2, and we have here resistance R, and this R equal to, let's say, 5 ohms. Okay, and now what will happen for the current? Actually, the current will be also random variable, because the voltage here is random variable with this distribution from -2 up to 2. So the current also will be random variable, and because we know that current equal to the voltage divided by the resistance R, so it will be that V, it will be -2, it will be -2 divided by 5. Okay, so the current here, because when the voltage is negative, it will change the direction of the current, because we know that minus or plus representing the direction of current, ampere, and the maximum of this current will be actually this 2 over 5. So the current will be alternating from 2 over 5 ampere and minus 2 over 5 ampere, and the sign here representing the direction of the current in both directions. Okay, so this is, and if you look for the power, so the power will be V squared divided by R. And now what will be the distribution of the power? If we have the distribution of voltage, what will be the distribution of the power B? Because the power B will be also a random process in this case, or random variable. And in this case will be like V squared divided by R. What happens if we have the random is random from -2 to 2, and it has V squared? Actually, now we have what is known as like mapping of random variable, and this will be the second lesson after this one. We will take it today, inshallah. But now let us come back to this question. But I like to sometimes to just forecast something that we're coming to, but just I throw some ideas or some questions. So I need you all the time to think with me also. Okay, so if V squared divided by R, how is the power will be also continuous? Is it? Of course, we don't have negative power. So how will be the shape of the power in this case? So this question, keep it in mind until we come to it later. Okay. Yes. If we come to the, and there is another distribution, is called exponential distribution, as we can see. So I will share the slides. So now we have already seen this, and we explained them. This one, and this is the uniform distribution. There is one example. It is exactly the same as the example now I was explained, but here we have random generation from 0 to 5 volt with uniform distribution. At a certain time, you take a sample from the output voltage. What is the probability that the measured voltage is less than 3? So it is the integration from 0 up to 3. Why it is 0? Because the minimum voltage here is 0. And from 0 to 3, why it is 1 over 5? Because the area must be 1. And then we can calculate all these probabilities. Okay. Here we have seen that the probability for exact voltage, because it is uniform, it is always 0. Okay, and we explained this last lecture why. And also the probability of something outside our range, it will be also 0, because the voltage here, it was given that it is from 0 up to 5. So it is not possible to be greater than 5. So the probability that you will get sample greater than 6, for example, will be 0. The next distribution, it is also uniform or continuous distribution, is called exponential random variable. The exponential random variable is defined as a positive distribution, f of x, which is equal to lambda e minus lambda x if x greater than or equal to 0, and it is 0 if x less than 0. So it means that it is always in the positive side. Okay, what is the the CDF of this distribution? The CDF, we take the integration from 0 up to a, lambda e minus lambda x. So we know that the integration of e minus lambda x dx is equal to, you divide by lambda, and by minus lambda, it will be minus 1 over lambda. Okay, e minus lambda x. And then we take the integration from 0 up to a. Okay, so we substitute first with a, so it will be minus 1 over lambda. Remember that we have outside here, we have lambda, so it will be lambda divided by lambda. Okay, and then you substitute for a, so it will be minus lambda a minus, when you substitute x equal to 0, so e of the power 0 equal to 1. Okay, so this will be cancel lambda, so we have sign here we have minus, so it will be 1 minus E minus lambda A. So this will be CDF, the cumulative distribution function of the exponential distribution. If you draw the exponential distribution, you will have such kind of shapes depends on lambda. As for example, for lambda equal to 1, as you can see here, you will have this blue line. For lambda equal to 2, you will have this red curve. And this is the CDF. So you can see that the CDF always is starting from 0 and approaching 1. This is for any random variable. Any random variable, discrete or continuous, the CDF starting from 0 and ending to 1. Okay, so you have to take this into like as a rule, starting from minus infinity with the probability density function, or with the random variable is minus infinity. So the CDF will be 0. Okay, and when it goes approaching infinity, it will approach 1. Okay, because CDF is the probability that x to be less than or equal to certain x0. So what is the probability that x to be less than infinity is 0. What is the probability that x to be less than infinity is 1. So the probability that x less than minus infinity is 0, because cannot be less than minus infinity. And to be less than infinity, of course, it is a real number. So it should be less than infinity. So it is 1. So this is general for the CDF. Always they have like this similar curve. But of course, depends on the process itself. So the curve can be something like that. It can be in discrete case. It can be something like that until it reach 1, and then it will continue to 1. It can be something like this. It can be something like, but always it is, and going, of course, it should go to 1. So it can be like this, going to 1, whatever. So it is always increasing function from 0 up to infinity. Okay? For any distribution, for any random variable. Exponential distribution, it has special application. Sorry that sometimes you can find wrong mentioned slide number, because these lectures was taken from one course, another course, and in that course we use like one package of slides. It was about 180 slides, and I distribute them over different lectures here, so you might find the wrong number. But it is mentioned the random variable of the exponential distribution that we mentioned before. So here it is, it has some like interesting application in the practice. So the distribution here is the distribution for time. So what it means, here is the distribution of an event, certain random event will happen. So let me come back to the same example that I mentioned before. The probability that a certain computer will be now just switched off due to some malfunction. It can be due to some physical or hardware defect or software defect. But now what is the probability? And now for certain computer to switch it off due to some problem. Okay. This probability, the distribution of the time following this exponential random variable. Okay. Now for certain computer, let's say that you have like maybe HB computer that you have, and based on the HB computers, they found that this lambda, the rate of like a crash, the rate of software crash or hardware crash in the computer. So the rate they found that it is, let's say, 0.001 per, let's say, year. Just example. Okay, I think it is very small to be that one. It means that in every year, on the average, for every year, out of 1,000 computer, there will be only one computer will face crashing, either in software or hardware. I think the number should be greater than this, but let us take this as example. Okay, so the distribution now of a computer to be crashed will continue or will follow this equation. Okay, now you want to use this equation. What you need to do actually depends on your watching time. For example, if you are interested to compute what is the probability that your computer will crash, or the time when your computer will crash, okay, like within 1 hour or within 2 hours in our lecture. Lambda here is given in terms of years. So what you need to do, the first thing, you have to be compatible between the value of lambda and your time or your watching time. Either you convert these hours into years, or you convert this lambda into how much per hour. Okay, now if I look to convert to this lambda to per hour, so in this case, lambda, I said that it is 0.001 per year. So I will divide this by how many hours in the year. It will be 360 days times 24. Okay, so this maybe I don't have calculator beside me, but let's say that this will be, let's say, as example, some 0.00001 per hour, for example. Okay, now I convert lambda into hour spaces. Okay, now the distribution, this will be the distribution. If you want to calculate what is the probability that the time where you will have a failure is within 2 hours, then you take the integration of from 2 up to 2 hours, and you substitute with this new lambda, because this new lambda now is given per hour. So you put here 0.00001, and this will be E minus 0.0001 lambda d t dt. Now, when you take this integration, I can calculate the probability that the time for failure will happen within 2 hours. If I like to calculate what is the probability that you will have a crash in your computer within like 1 day, of course, simply you can take the integration, but over 24 hours. So this exponential distribution gives you the capability to have the distribution of the random time. So it gives you the distribution of the random time, and this could be used for any event that I am interested, that what is the probability that I will have some event happen within like 1 minute or 5 minutes or 10 minutes and so on. And it is very, very useful in simulations as well. So when I like to make some emulation for some failures happen, okay, and now I like to emulate, for example, power system, where we have generators, we have circuit breakers, we have many other items there, and then the failure can happen at any time of these items. Okay, then I like to calculate the probability that I will have failure at certain time. So I can generate the failure time according to the generation of this exponential random variables, as we will see maybe next week when we show some Octave or MATLAB simulations to simulate or emulate some events. We have another distribution, it's called gamma distribution or gamma distribution, and this is actually nothing but just the summation of exponential random variables. What I mean, assume that we have a system, that this system consists of several items, okay, and assume that the probability for each one of them or the distribution of the time required before a failure is happened for everyone is given by exponential distribution. So for example, this is system 1, system 2, system 3, and system 4. And then we have here T1, T2, the time where there is a like failure happened. This is T3, and then T4. Okay. Assume that this system will be out completely in outage if all of them they got like failure. Maybe they are connected in parallel. For example, assume that this system connected this way. This is T1. This is T2. This is T3. This is T4. Okay. And we have summation here. So in this such for high reliable system, so we have like 4 systems connected in parallel, and we know that the failure of the whole system will happen if all of them get failure, all of them. So now I am interested to look to T capital K, the time. I am looking to find the distribution of the time Tk, which is nothing but the summation of each time, summation of each one. Each time now is a random variable. Each one is a random variable. It doesn't mean that T1 is greater than T2 or T2 is greater. No. Each one has a random variable, independent random variable. And each one, the distribution following exponential distribution that I explained now. Okay. Now I am looking for the distribution of the time Tk, which is the summation of all these times. For example, T1 plus T2 plus T3 plus T4. What is the distribution of this new time? Because this new time, it is also random process. It is also a random variable. I am sometimes using swapping between random process and random variable. Actually, random process when we have a time, when we have some independent thing, which can be time or it can be space or it can be whatever. But maybe here it is more precise to say random variable. Okay, even it can be random process as well. Here it is T capital is the summation of this T1 plus T2 plus T3 plus T4. What is the distribution of this T? The distribution of this T is given as gamma distribution. And the gamma distribution, as you can see, here we assume that all lambda for each one is the same. Everyone has the same lambda, the same rate. So we have lambda times lambda T of the power K minus 1 E minus lambda T divided by K minus 1. So this distribution is known as gamma distribution. Okay. Don't be confused that what is this and why we apply this. Actually, it comes later. It comes when you face it. Maybe in when you arrive to the stage of writing your thesis, you might have some problem like that. For example, you have summation of encoding techniques. For example, you have a couple of you retransmit the same symbol several times, and what is the probability that all of them they will arrive in like, for example, outside certain time, the time of the delay. Then in IoT application we will have large delay in the IoT integration, in IoT, Internet of Things, okay, where we have some sensors, and those sensors sending signal with wireless communication to some controller. The controller needs to receive the signal within T to be less than some T maximum. Okay, and we know that the signal, it might arrive with different delay, different latency. So we send it with different like paths. So what is the probability? What is the probability that T is less than T maximum? That we will receive it correctly, or the reverse, of course, T greater than T maximum, and this will cause instability problem. And T here is equal to the, for example, it can be the minimum time of all these times, or in some problems that you are interested to see what is the summation of Ti from I equal to 1 up to K, and the distribution of T in this case will be this gamma distribution. Actually, I have seen a lot of or many PhD thesis and also master thesis where the student just try to formulate his or her problem to follow certain distribution like gamma distribution, and after that they start to solve it with some several pages of mathematical manipulations in order to get the final result, and then they got the probability of instability in certain control system. It is called networked control system. And then after that, when they compute that, they make simulation, and after the simulation, they compare the simulated result with the theoretical result, and then it can be considered as very nice like paper, which can be published in good journal, and it can be also one piece of important PhD thesis, or it can be in excellent master thesis, which is actually based on these simple concepts. The idea is that I like you that to have these skills, the skills of dealing with such equations and how to make your problem and how to justify that the problem that you are studying is following certain one of these like probability models, and then how to solve it and how to simulate it. Then you will have your master easily, you will have your PhD, you can have you can publish papers, even you can publish paper every couple of weeks if you like, when you master these techniques. Okay, and I can show you that it is not hard to. What you need is to practicing yourself. Just as one of you contacted me, so I advised him that you can go to the internet. If you write, for example, solve the problems in a probability or in probability density function, you can find a lot of them. You can. I remember when I was studying these things in bachelor stage, there was one book. It is one of the Shom series, and it was about probability and stochastic process, where it has a lot of solved problems. And so try to practice yourself. Of course, practicing and solving problems, it doesn't mean that the student like grabs the concept. So here, you might observe that I concentrate or I focus more about the concepts, and then the ability to solve problems. It can be improved all the time by using many resources, but it is hard to like catch the major concept or the main concept by just solving problems. Solving problems makes you easy for you with hand calculations, but you might not get the main concept of that. Okay, uh, now we come to the one of the most important random variables. It's called Gaussian distribution. And this Gaussian distribution, actually, it has a lot of main or very important applications. Almost, for example, noise in our area in telecommunication, white noise is Gaussian distribution. Okay, uh, many problems. Actually, I could say most of the practical problems can be approximated as Gaussian or normal distribution. It has secret benefits, actually, and it has like hidden power, this distribution. I just show you a few of them. You know that if you have any random variable, y, and this y is a summation of many different independent random variable like x1 plus x2 plus x3 plus xn. So we have many of them. Each one of them is a random variable, okay, independent random variable with any kind of probability density function. Any probability density function. Anyone, it has different, or it can be the same or different probability density function, but they are independent. There's no like dependency between them. So when you take the summation over infinity number of these distributions, the result will approach to be Gaussian distribution. This is called or normal distribution. It is the same. Sometimes they call it normal distribution. We in telecommunication, in communication area, we use the Gaussian distribution, but in statistics they use more normal distribution. Okay, so this distribution actually is the summation of any random processes or random variables with independent random variables. They will always like converge to be Gaussian distribution. This is called central limit theorem. This is called central limit theorem. Actually, many like real or realistic behavior could be distributed as Gaussian distribution. Even the shape of Gaussian, you can see the shape. So we have always the mean. The mean is many people approaching close to the mean, and then if you go here and there, then the probability will be decreased. As you go away from the mean, the probability will be decreased. And here we have the tails. The tails, the probability that will be very close to zero. Of course, depends on the variance. The variance of the distribution depends on the variance of the distribution. Okay, we will talk more about variance and about the mean when we come to that subject of the expected value, the averaging or the expected values. Okay, so for example, if we take the any like real issue, for example, the size of shoes, for example, we know that the size shoes can be maybe for babies can be maybe 10, maybe, and maybe it can be up to 49 for some people that they have very big foot. Okay, and now how the companies will manufacture sizes. So what sizes that they will use? They look what is the mean. For example, for men, the mean is around 42 point maybe 5. This is the mean. Okay, for men, for adult men. Okay, and then you can see that the manufacturing rate of shoes manufacturers, usually they follow this curve, and maybe very rare, because very rare that we will have like 49 or greater than 49. So in that case, they don't produce them sometimes at all, unless based on some special request. Okay, but otherwise you can find in the market that most of them will be for example men shoes that will be, let's say, from 40 up to 45. If you go to females, you can find maybe between 36 maybe up to 41, most of them, because now they follow this shape of Gaussian or normal distribution. The IQ of people, or the how smart human for the human thing. So you can see also that it will have this normal distribution, and maybe you can find very few percentage where they can be more than certain IQ number, maybe 120 or 130 or 150. I don't remember now the numbers they use. Then you will find that very few people they cross this number, and most of the human they are, or people, they are located around some mean. So this is the mean, okay, of the average of the Gaussian distribution, and the width of this average is called the variance. Okay, and also and this is the mean, and it is symmetric. This symmetric distribution means that the distribution is identical after the mean and before the mean, and also it is mean in Gaussian distribution. Mean is the same as median, is the same as mode. So all of them, they are the same for Gaussian distribution. It is very important. This Gaussian distribution actually is one of the most important distributions that we will use. Also, many different distributions can be approximated as Gaussian. Okay. The last thing today that I wanted to show, yeah. After that, what is this? For this multidimensional Gaussian, we will skip it now, because we will come to it back when we come to the estimation theory in the next part of this course. Okay, so we will come back to this part. But what I wanted, okay, this is the functions of random variable. Actually, I will postpone this to the next lecture. I will not go to the function distribution, but I will end this lecture today with this Q function, or with this actually normal distribution. I will together try to evaluate what is the CDF of this distribution. Okay. back to the, yes. So we said that Gaussian distribution is a distribution which has this shape, 1 divided by square root 2 pi. Okay. Then we have here sigma. Sigma is is called standard deviation. Sigma square is the variance. Okay. And E minus x minus mu. Mu here is the mean. Mean, median, mode, the same. Square divided by 2 sigma square. Remember, in normal distribution, mu is mean, the same is median, and the same is mode. And sigma equal to the standard deviation, and sigma square, if you take the square, it becomes variance. Variance, yes, of x. Okay. Yes. So now we have this distribution. We show that it will be something like that. And here is x. The variance gives us the width of this flipped bill, and or inverted bill, and then shape, and this is mu, and this is related to sigma or sigma square. Okay. Now we like to calculate the CDF of this one. What is the CDF? CDF is the probability, or F, let's say, of A is the probability that x to be less than or equal to A. And this equal to integration from minus infinity up to A. Of course, 1 divided by square root 2 by sigma. Those are not function in x, so we can take them outside the integration. Simple. And then we have here E minus x minus mu square divided by 2 sigma square dx. Okay. We have a problem here that in general, the integration of x square, e to the power x square, does not have like closed form solution. So the integration of e for any number, for example, let's say alpha times x square dx, this one doesn't have a closed form solution. So we don't have the result of this integration. Okay, there is no, or in other words, the result of this integration cannot be represented in like conventional math that we know. Okay, the normal equations like trigonometric functions or polynomials or whatever, or logarithmic, it cannot be represented. This function cannot be represented in shape of any trigonometric or exponential or logarithmic functions or polynomials. So in that case, we don't have the closed form solution for this one. How could we evaluate this equation? Okay, now we can let us define another like variable t, and this t equal to, we say that this t equal to x minus mu divided by 2 by square root of 2 times sigma. Okay, you can see here this is the same as that one, t, and in that case, if we substitute here, we know that dt will be 1 divided by square root of 2, okay, times dx. We can take this one and substitute in the previous equation. Then what we'll get that the CDF will be 1 divided, because square root of 2 with dx, it will be dt. So we will take off the square root of 2, but we will have square root of pi only, sorry, square root of pi times sigma, okay, integration e minus t square dt. Why? Because t, you can see here, t is x minus mu divided by square root 2 sigma. So when you take t square, actually all of this is t square. Okay, and now dt is equal to dx divided by square root 2. we take the square root 2 with dx, and it becomes dt, and then we will have this e of the power minus t squared. But here we will have from minus infinity up to a. So if you substitute x with minus infinity, t will be also minus infinity. Okay, when we substitute a with x with a, so it will be a minus mu divided by square root of 2 times sigma. So this will be from minus infinity up to minus, and this, as we see, this will be a. So it will be a minus mu divided by square root 2 times sigma. This will be the integration. What is the benefit of putting it in this form? Now we have the standard form, because this one, it will be the same as this one will be, because if you take from minus infinity up to 0, this one will be half. This one will be half. But now we have it as general shape, where we can generate this one by using tables. So we have a lot of tables, like it is called error function tables, that we can find the values of the CDF. Why we use the tables? Again, because we don't have closed form representation of the form of e to the power x squared. So if we go back to the slide, so you can see here that it is the same as we did now. This is the shape, 1 divided square root by e minus c squared dt. And now we can take from minus infinity to 0 is equal to half. Why is equal to half? Again, because it is symmetric. Since it is symmetric, so from my and the mean here is equal to 0. So it means that from minus infinity to 0 is equal to half, plus half error function of this value. What is the error function? This is the shape of the error function. And the error function, you can find them in tables. The value of the error function, you can find them in ready tables. But right now, we don't use those tables. Right now, we use just MATLAB or Octave in order to find the value of the error function. So you can just write error function of any value, so you got it. So you don't need actually to use the tables anymore. Yes, this is the CDF of the Gaussian distribution. And in telecommunication, we use Q function more than error function. Error function is used in the statistics a lot, but in telecommunication, we use the Q function. Actually, the Q function is nothing but computing the tails, the probability of the tail of the Gaussian distribution. So you can see that the Q function is defined as the probability of the tail. It means that if we have this distribution, and what is the probability that x to be greater than the probability that x greater than or equal to x0, for example, this is x0. Okay, because this tail usually in telecommunication representing the probability of error. So the probability of error can be directly connected to q of x, and due to that, we use this standard form. So the standard form that we use in telecommunication is not the error function, but the Q function, as it is shown here. Okay, and however, they are related actually. A Q of x is half error function complementary of x divided by square root of 2, and error function complementary of error function, it is already given here. We don't need to rewrite it again. So the error function complementary, or the complementary of error function, is 1 minus the error function. 1 minus the error function. So the error function that we show now, we can use it directly to compute the Q function. Okay. Here it was given that a random signal x of t with Gaussian probability density function, the mean was given that x of t equal to 1 volt. The variance was 4 volt square. Okay. And by using a Q function table, find the probability that x to be greater than or equal to 0.5, x to be the voltage to be less than or equal to 5, and x to be between 1 up to 3. The first thing that we need is to convert this Gaussian to the standard form. And to convert it to the standard form is simply you define, and this is valid for any distribution that probability Gaussian distribution that we will see later. So you convert it to the standard form is that z equal to x minus mu x divided by sigma x, and sigma x was given because variance equal to 4. It means that sigma, the standard deviation, is the square root of 4 is equal to 2. Okay, and then mean is equal to 1, so it will be x minus 1 divided by 2. And then we like to calculate what is the probability that to x to be greater than or equal to 2.5. So now x, we have this x minus 1 divided by 2. So it means that because we cannot use x directly, as I said that the normal distribution or Gaussian distribution, it doesn't have a closed form. I need to convert it to some of the standard forms. Then now I convert it to the standard form. So z equal to 2.5, I use here 2.5 minus 1 divided by 2. So what is the probability that z to be greater than or equal to 2.5 minus 1 divided by 2? And this means that it is the Q of 0.75. Those are the tables that you can find in books or the internet. But as I said, that you don't need to use these tables because they are already now. You can use some function in the MATLAB or Octave, or also some advanced calculators that you can use. So the Q function now 0.75. Here we have 0.7 is 0.24, 0.8 is 0.21. So it is something between. So it is around 0.22. This will be around 0.22. And what is the probability that x equal to be less than or equal to 5 is 1 minus probability of that x greater than or equal to 5. And then again, it will be 5 minus 1 is 4. 4 divided by 2 is 2. So it is 1 minus a q of 2. A q of 2, if we look here, this is a q of 2, 0.0227. So it will be 1 minus 0.0227, and this will be about 0.98. So this is actually the way that we can calculate the calculations related to the Gaussian distribution. And the idea here that we convert it to the standard form. Just to make sure that you understand what I mean here, that this is the standard form of the Q function. The general form of the normal distribution is 1 divided by square root 2 of pi times sigma integration from x to infinity e minus x minus mu divided by 2 sigma square, and here we have square. Okay, now compare this equation with this equation. You can find that if you take t equal to x minus mu divided by 2, 2 is there already, divided by sigma, so it will be the same. If you take t equal to x minus mu divided by sigma, those two equations are the same, because when you take the integration, dt will be dx divided by sigma. So dx divided by sigma, it takes each other, it becomes dt. This is dx, okay, and then we have exactly the same form. But this is the standard form, the general form, and this is for our like problem. Okay, so what we need to convert any shape to the standard form, and the conversion is done by taking this equation, t or z or whatever, equal to x minus mu divided by sigma. So for any distribution, if I give you any distribution, like I say for example, you have normal distribution with mean equal to 5 and sigma square equal to, let's say, 100, and calculate the probability that x to be, for example, greater than or equal to 7, for example. Okay, simply you convert from the general from this specific form to the general form. How to convert to the general form? You define z or t equal to x minus mu divided by sigma. It is simply like that. Okay, what is x? Here x is the number that we are looking for, minus mu. What is mu? Mu is here 5. What is sigma? Sigma is the square root of the variance, so it will be divided by 10. Okay, I am looking for what? I am looking for x to be greater than or equal to 7. Then it is the same as probability that z greater than or equal to, I substitute instead of 7, instead of x, I put 7 here. So it becomes 7 minus 5 divided by 10. So the probability that z greater than or equal to 7 minus 5 equal to 2. 2 divided by 10 equal to 0.2. So simply it is the same as a q of 0.2. Okay, so this is the way that we can solve for any Gaussian distribution or normal distribution from any specific case. We need to convert it to the standard form, and then we make the calculations. Okay, I can finalize by another example. I will finalize by another example now. Now we have what is the probability that x to be let's say less than or equal to 2. Okay, and you have the normal distribution with mean equal to 1 and variance equal to, let's say, 16. Okay, I think number that we can have the square root easily. Okay, now we have x less than or equal to 2. So actually this is the CDF. This is the CDF f of 2. Okay, so if you have the error function, you can of course directly compute it from the error function as we saw before. But if you want to use the Q function, then I can use also the Q function. Here I will show how to use it with the Q function, because you are from telecommunication. So in telecommunication we use the Q function more than error function. Okay, now again we come back to the standard form. The standard form is called Z equal to x minus mu divided by sigma. Okay, mu here is equal to 1. Sigma here equal to 4. The square root of 16 is 4. So it becomes x minus 1 divided by 4. Now I convert it from the specific form to the standard zero mean form. Now I take this and calculate. So the probability becomes that z greater than or equal, sorry. Here we have probability that z to be less than or equal to. Okay, and substitute, this will be 1. 2 minus 1 is 1 divided by 4. But remember, this is not the Q function, because this is less than or equal to. Q function is greater than or equal to. But it is not a problem, because this one equal to 1 minus probability of z greater than or equal to 1 over 4. And this will be 1 minus a Q of 0.25. Okay, and then we can find from tables what is Q 0.25, or you can find it in MATLAB. Then 1 minus this one, you will have the probability of this event. Okay, yes, so I think that's all for today. I don't need to complete the slides. So it is we will complete them when we go. Let me just, yes. Okay. If we return to the slides. Yeah. So this is actually the just octave calculation. So please, when you run n, you can have Gaussian distribution in MATLAB or in Octave. I will come back, inshallah, to this next lecture next week. And also after that, we will next week we'll start by functions of random variables. So if you have function like y equal to function, not distribution, function in x, okay, and x is a random variable, so how will be the distribution of y? This is the question now. If you have, let's say, if you have y equal to x squared, and x, it has distribution f of x, what will be the distribution of y? This will be the question that we will answer next week, inshallah. And after that, in this part, here is functions of in case of vectors, but also this part I might skip at this moment and come back to it later, with especially in estimation theory. Here we have another distributions. Also, I will talk about them next week, like Rayleigh distribution, chi-square distribution, and the Kagami distribution or Rice distribution. They are very important in telecommunication area. So we will talk about them later. And then we continue to, in the lecture 5 also to talk about expected random variables. This is one of very important also part, that how to find the expectation of any random process. And the expectation means that you are like forecasting or predicting what will be the value, what is the expectation of the power, for example, of certain signal, and so on. This will be the topics of next lecture, inshallah. And that's all today. And sorry today that, as I told you, that I have this little bit flu. So, but I hope that you will able to continue with me and concentrate. Okay, so I will stop recording.